Hello, Precalculus student. This video is for chapter 4.7, exponential growth and log models. And we start off with exponential growth models, talk about growth of population, also growth of money with compound interest in example 4. And then we're going to do example 5, which is continuous growth. That means compound interest will be given to the account continuously. So there is an initial deposit of 32,000 and it increased by compound continuously at this rate of R equal to 5.5%. In decimal is 0.055% or 0.055. Okay, find the amount after 18 years. So we just use the model, right? So in 4.1, we talk about if it's compounding continuously, the model is A, the amount after T years would be AC or P, which is 32 initial deposit, E of 0.055, and then T is years because the rate is year. So then you just need to plug in. So replace this B by 16, 0.055, not 16, 18. So put the calculator. Okay, so 3200 e to the power 0.055. Yeah, we need to do the parentheses because I need to multiply by 18. x611.95. So the amount of money is x611.95. It round in cents, round to the nearest cents. And then how long does it take for the account to double? So doubling time is the same as what we have talked about in population, ln2 over k, right? So k is the continuous growth rate, so it'll be ln2 over 0.055. ln2 divided by 0.055. 12.6 years. So this is a very convenient thing. If you know the rate of an account that is compound interest or compound continuously, of course, compound continuously is grow a little faster, but you can use it to approximate the doubling time. Okay, how long does it take for it to grow to 8,000? So initial value was 32,000, so 8,000 would be A. 32,000 is initial. E 0.055 t, right? So this is solving exponential equation again, divided by 32,000 on both sides. So we can say 80 over 32 because we divided 100. We can simplify it a little bit, but not simplifying, but do not write it as a decimal number. So E 0.055 t. So again, to solve for t in the denominator, do ln because I have a base E. Right, so that means ln 80, or actually 8 over 3, we can simplify more, equal to ln E 0.055 t. Once it is behind a log, this can move outside. So my t would be equal to ln 8 over 3 divided by 0.055, and that's the time it takes for it to grow to that much. So 8,000, oh no, what was it? ln 8 over 3, 8 over 3 divided by 0.055. 17.83 year. So that's year because the time period is year. 17.83 year for it to grow to 8,000. Okay, so the third model that we are looking at is exponential decay. Now, exponential decay, the function formula is no different from exponential growth. It's still A0 e to the kt, but k is negative. If k is negative, it would be a continuous decay mode, and A0 is the initial value. Again, we also can find half-life using this. You would say half of A0 because it's decreasing, right? So after some period, it would become half of it, kt. So we cancel A0 by dividing on both sides. So that means it's 1/2 E equal to kt. To solve for k, or to solve for this t, this is the doubling, this is the half time. So we do the same thing. ln 1/2 equal to ln E of kt. kt can move out. So that means ln 1/2 is equal to k times t times 1, right? So t would be ln 1/2 over k. And remember, k is negative. K is negative. But ln 1/2 is negative, so your time would be positive. And vice versa, if we know the half-life, we can also use a half-life model, A0 1/2 t over t, where t is half-life. So these are the steps to solve for exponential decay model. So if you know the whole A0 and K, you can just plug in. If you don't know A0 or K, but you have some values of T and Y, then you can solve the system's equation. To find half-life, you do ln 1/2 over K. So these are the typical things that you would use to solve an exponential decay uh, question. First one, medication of 80 milligram decay continuously in the patient's body after your body digests it, or being injected into the body, you would dissipate because the body would use it, right? 80 milligram decay continuously at a continuous rate of 40% per hour. So every hour it would remove 40% of it. Write the model that models the medication remain after T hours. So we would use Y equal to A0, 80 milligram, E to the 40% is 0.4, right? 0.4 T, where T is in hours. So T, remember hours. So now, so this is the model. Okay. And then what is the second thing? How much would it be in the patient's body after 5 hours? So after 5 hours will be 80 E of 0.4 times 5. So that would be the amount. This is just a plug-in, right? So I have a lot of these things. Just do it. 80 E to the power what? 0.4. Okay, so I want to multiply time what? 5. It is hours, so times 5. 5. Oh, negative. I forgot. It is a decay, right? Negative. Oh, I think I forgot that one too. It should be negative because it's decay. This would be growing. No wonder it's become more. So it will be 10.8 milligram. After 5 hours, you only have 10.8 milligram in your body. What is the half-life? That means how long would the 80 milligram become 40 milligram? Is ln 1/2 over k, negative 0.4. So let's try ln 1/2 over negative 0.4. 1.73 hours. Very similar to exponential growth, except k is negative. Example 2, a 560 milligram of a radioactive compound decays to 400 milligram after 80 minutes. So this is the case where they tell you the initial amount. This is A0. And then a future amount, but you don't know the function. So to find K, right? You would say, okay, so I have 400 is Y, right? Y, this is Y value. And this is the time. So you have Y equal to 400 equal to 560, A0, e to the negative. Oh no, we can just say K. We know that it is negative. K times 80 because in minutes. Okay, and remember it's in minutes. T in minutes. In minutes. Keep track of it. Okay, so to solve this, I divide to solve for k, I divide this. So it become 40 over 56 equal to E of 80k, 80 minutes. So ln 40 over 56 equal to ln E of 80k. 80k can move out. So k would equal to what? ln 40 over 56 divided by 80, right? So that's what we do. ln 40 over 56 divided by 80. Oopsie. Divided by 80. Negative 0.004206. 0.0042. 4206. 0.004206. So 6 decimal places. What is the half-life? Half-life would be ln 2 over k, right? So no, ln 1 half. Look at the double. So ln 1 half divided by, the model. We need to write the equation. So the equation is y equal to 560 e 0 negative 0.004206 t. T is in minutes. Over 0 negative 0.004206. ln 1 half divide negative 0.004206. 164.8. 164.8. No, 164.8. What is it? In minutes. So everything, the time is in minutes. The third example is again radioactive decay. So there is a americium 241. It's kind of those radioactive compound. Has a half-life of 482 and an initial value of 800. So this is very good. 800 is here, and this is t of half, right? We just call it t. Write the function that model the remaining of t years. Because we have half-life, we can write it as the half-life model. So we will say y is equal to 1 half. No, y equal to A0, which is 800, 1 half of t divided by 482. Okay, and if I want to use the other model, we can say ln 1 half over our half-life 482. So that would be, I can just use this half-life ln 1 half 482 negative 0.001438. Negative 0.001438. So we can also write as y equal to 800 e to the negative 0.001438 t, where t is in year in this case. How long does it take to decay to 90% of the initial amount? So the initial amount is 800, right? Equal to A0. 90% of it is 90% times 800 is 720. So we would say we need to solve 720 equal to 800 e to the negative 0.001438 t. We want to solve for t. So divided by 800 on both sides. So this actually divide totally is 0.9. Negative 0.01438 t due to ln 0.8 equal to ln e negative 0.01438 t. Move this up in the front. T would equal to ln 0.9 divided by negative 0.001438. Put in the calculator. So can I finish it in time? ln 0.9 that by 0.00